Welcome to The Explainer. If you've ever found yourself wondering how we actually make the leap from simple, old-school predictive equations to the massively complex engines that power today's artificial intelligence, well, you are in exactly the right place. Today, we're going to open up the hood and unpack exactly what a neural network is, how it actually learns, and why it represents such a massive, fundamental shift in how we handle data.
So, let's set the stage with a really common high-stakes business problem. Imagine Sarah, a data analyst at North Star Retail. She's staring down a fascinating challenge. If we track detailed customer behavior data, every click, every page view, every time they add something to their cart, can we predict if they're actually going to finish checking out while they're still actively shopping? It's a classic real-time prediction problem. And if you solve it accurately, it means a huge boost in revenue, because you can step in with a targeted intervention, like popping up a discount code right when they're hesitating.
Looking at her Monday morning data, Sarah's got a solid set of 8,000 customer sessions. And what's really interesting here is how this data is structured. She's working with 9 behavioral features, things like time spent on the site or if the user is a returning visitor. But hidden in there is a massively dominant signal: items added. It probably doesn't shock you that sessions where people actually put stuff in their carts end up in a completed checkout way more often than sessions with empty carts. Her target label is straightforward, just a binary 1 or 0. Did they check out or didn't they? So why does this matter for your own projects? Because identifying that dominant signal right out of the gate is absolutely crucial. It saves you from chasing ghosts in the noise later on.
Now, before throwing some crazy, complex AI at the problem, Sarah does a smart thing and establishes a baseline using a simple, classical logistic regression model. This baseline achieves an area under the curve, or AUC score, of about 0.76. To put that into perspective, an AUC of 0.5 is basically a coin flip, and 1.0 is absolute perfection. So at 0.76, her model is doing a pretty decent job of ranking sessions, but it's definitely not perfectly separating the actual buyers from the window shoppers. That 0.76 is our bar to beat.
To beat that baseline, we first need to wrap our heads around the fundamental building block of neural networks, the perceptron. Think of a perceptron as just a single artificial neuron. It takes in various inputs, like those 9 behavioral features, assigns a weight to each one based on how important it is, adds them all up, and then uses that total sum to draw a rigid, straight line right through the data to separate the buyers from the non-buyers. Actually, logistic regression is basically just a single perceptron in disguise. It's incredibly fast, but its absolute hard limit is that it can only ever think in straight lines.
And that limitation is a real deal breaker for complex data. A single straight line completely fails on nonlinear patterns. Think of the famous XOR logic problem, where your target points are sitting in opposite corners of a square. Try it. There is no single straight line you can draw that will separate those corners. And that is exactly why we stack these neurons up into what's called a multi-layer perceptron, or NLP. By sandwiching a hidden layer of neurons between the input and the output and injecting a mathematical kink called a nonlinear activation, we give the network a superpower. It can now bend and curve its decision boundaries, wrapping around incredibly complex, nonlinear patterns that a single straight line would completely miss.
Walking down the mountain. How networks learn.
Okay, so we have this curving, bending network, but how does it actually learn? This brings us to a beautiful concept called gradient descent. Imagine you're trying to walk down a really steep, rocky mountain, but it's pitch black outside. You can't see a thing. The landscape around you is what we call the loss surface. Basically, it's a measure of how wrong your model's predictions currently are. Because you're in the dark, you have to carefully feel the ground with your feet to find the slope. That slope is the gradient. Once you feel which way is pointing downhill, you take a step in that direction. You evaluate your new spot, feel the slope again, and take another step. You literally just keep repeating this, stepping downhill until you finally hit the valley floor, which represents the lowest possible error for your model.
Now, the really tricky part of this mountain descent is figuring out exactly how big of a step to take, which deep learning folks call the learning rate. If your step size is way too big, you'll confidently stride right over the valley floor and end up way higher up on the opposite mountain peak. Your model's learning will just wildly diverge. But if your step size is too small, you're just taking these millimeter-long shuffles. Sure, you'll eventually get to the bottom, but it's going to take forever and waste a ton of expensive computing power. You need a Goldilocks rate, not too big, not too small. Luckily, modern tools like the Atom Optimizer act almost like smart hiking boots, automatically tweaking your step size for every single parameter as you walk, completely removing that manual tuning headache.
But wait, how do you actually calculate that slope when your network has hundreds or even thousands of parameters? To figure out which way is downhill, we rely on a process called backpropagation. I know, it sounds super intimidating, but conceptually, it's actually incredibly elegant. If gradient descent is stepping downhill, backpropagation is how we retrace our footprints backward up the mountain. In frameworks like PyTorch, this is handled by a magical feature called autograd. After the model makes a prediction and figures out how wrong it was, PyTorch literally walks backward through your exact computational path. It figures out precisely which step, which specific weight, caused you to stumble, and it assigns the exact right amount of credit or blame for that final error.
And all of these concepts build directly into the famous 5-line PyTorch training loop. It's this beautiful, repeatable pattern that drives almost all of modern deep learning. First up, Optimizer.ZeroGrad wipes the slate clean, clearing out old gradients from your last step. Second, the forward pass pushes the data through the model so it can make a prediction. Third, we compute the loss, which just measures how wrong that prediction was. Fourth, lost op backward triggers our backpropagation, doing that backward walk to assign blame to the weights. And finally, Optimizer.Step acts as our gradient descent, taking that crucial physical step downhill to update the weights. Whether you're crunching a spreadsheet or training a massive world-changing language model, these 5 lines are the fundamental heartbeat of the learning process.
So, after setting up this awesome PyTorch neural network, Sarah tests it against her original baseline. And here is the highly surprising reality check for her Friday presentation. On this relatively small, mostly linear tabular dataset of 8,000 sessions, all 4 models basically tied. No way, right? The simple logistic regression, the deep learning MLPs, and the gradient boosting model all clustered right around that 0.76 AUC score. The super advanced deep learning model with all its parameters and complex backpropagation didn't magically crush the simple straight line model. Why? Well, because on small tabular data with limited nonlinear interactions, the algorithm you use rarely matters as much as the actual quality of the data itself. Seeing this, Sarah makes a truly brilliant business call. She decides to just ship the cheaper, simpler, and much more interpretable logistic regression model for this specific checkout prediction task. And honestly, this is a vital lesson for anyone working with data. You do not always need a massive deep learning sledgehammer to drive in a small linear nail. But hey, Sarah's work building that neural network absolutely wasn't a waste of time. It actually leaves us with a highly provocative question. Her boss was totally thrilled with the checkout model, but now wants to automatically tag unstructured product photos, categorizing raw images as dresses, jeans, or jackets. The simple straight lines of logistic regression are going to completely fail on a messy grid of image pixels. So how on earth will we use the exact same 5-line PyTorch learning engine we just built today to conquer the massively complex, nonlinear world of computer vision? Well, that's exactly what makes deep learning so incredibly adaptable, and we'll be tackling that very question next time.